So, last class we just concluded with the single phase half controlled rectifier. And then we introduced the resistive and inductive load. So, with inductive load, let us draw the diagram once again. This our mains, then we have the thyristor, our device, then this inductive, highly inductive load, we will assume. This is our, across this one we will say this is a V0 T. This point is our input. Let us draw the output voltage ripple with respect to a particular firing angle alpha. This is our axis magnitude, this is our omega t axis. Now we will draw our input sinusoidal voltage like this. Okay. We will be firing at this point alpha. Alpha we will be measuring from the 0 point to the instant of firing. This is alpha. Now, with the inductive load, the moment this thyristor is turned on, giving gate pulse, the input will be connected across the inductance. Now, if you see here, the current through the inductance cannot change instantaneously. So, the moment the gate rate is given, current will slowly rise such that the rate of change multiplied by inductance L into di by dt will be the voltage across the inductance, that is the mains voltage. Now, the device is on. At omega t is equal to pi, where our input mains voltage goes to the when comes to 0, what happened? The current through the inductance or the load will come to its maximum point, and thereafter it will slowly reduce. So, at this point it will be di by dt will be 0. So, that the voltage, input voltage and the load voltage will be, Kirchhoff's voltage will be matching. Then the moment voltage goes negative, so there is a current in the inductance. Current through the inductance cannot change instantaneously. So, what will happen? Unlike in the case of resistive load, the thyristor will not switch off immediately, and the stored energy in the inductance will make the current to flow again continuously. So, that slowly current will try to decrease from this point onwards. So, at what point it will come to 0? That depends on the inductance and the initial stored energy, that also that depends on the peak value of the current. Now this di by dt is negative. So, L into di by dt is equal to V in, assuming the diode drops is negligible. So, now the di by dt slope is negative from this point to this point. So, what will happen? The polarity across the inductance will change this way, that is true here also. Voltage has AC voltage waveform has reverse. So, Kirchhoff's law will match here also. Now, this voltage L di by dt minus this voltage. So, this voltage will force, minus this voltage will force this thyristor in the forward conduction stage, and thyristor will continue to conduct till the current comes to 0. The moment current comes to 0, the thyristor will switch off, because thyristor cannot conduct in the opposite direction. So, this point where the conduction has come to 0 is not in our control. It depends on the inductance and the initial load current, the maximum load current flown through the system. So, with various inductance, sometimes it can extend this way also, sometimes it can extend this way also. So what it means, we lose control. So we don't know what is the output ripple coming across the inductance. So the previous equation with the resistive load with the firing angle, we output with respect to firing angle alpha is equal to Em by 2 pi into 1 plus cos alpha is no more valid here, because there is a negative conduction, that is negative, that is the negative in the sense when the voltage, input voltage has gone negative. So for this equation, that is output DC value, to be valid here also, this negative side we have to remove. That means there should not be a conduction, or there should not be a negative ripple coming across the inductance. At the same time, there is another requirement. Current cannot stop instantaneously in the inductor. Current cannot abruptly change. So we should provide another path for this inductor. There, the concept of freewheeling comes. What it means, when this voltage becomes positive here, that is during this portion, if we want the thyristor to go switch off from this point onwards, at the same time we want to give an alternating freewheeling path across the inductance. What we can do, we can provide a diode here. So when the thyristor is forward bias, when the thyristor is conducting, that is during the positive half cycle, this point will be positive with respect to this point, and this is shorted because the thyristor is gate on, this diode will be reverse biased. So the current will flow through this way. The moment di by dt becomes negative, this diode will get forward biased and the current will freewheel through this path during this portion. That is, if we mark AB till C, AB region thyristor will be conducting, thyristor conducting. During the BC region, diode will be conducting. Now what will be the output voltage ripple across the inductance? If you see here, we can draw it here. If this is the input voltage V in, our V0 will be, if this is the firing angle alpha, our V0 or the voltage ripple across the inductance will be this one. Again it will repeat the next positive half cycle. So this voltage ripple across the load, now the load is, whether it is resistive or inductive, we don't have to worry. With this freewheel diode, automatically this voltage ripple will appear across the load, and this equation is valid for the output V0 volt. V0, that is a DC, this is a DC value with respect to firing angle alpha. Now if you see here, another problem with this case is, even though we can draw power from the mains, we are only drawing during the positive side. Negative side we are not utilizing. Okay, so maximum power utilization is not there. At the same time, if this is the V0, that is the V0 alpha VDC, there are ripple associated with the output voltage. So this ripple voltage, what is the frequency of this ripple voltage? It repeats every cycle. So this ripple voltage, this frequency component will have the fundamental, then third, fifth, all harmonics will be there. For higher harmonics, the impedance L omega will become more and the current drawn by the inductance is less. So if you want to have a pure DC, okay, we have the load. Even though I have mentioned this one purely inductive, mostly we will be talking this one in the context of DC motor drive application. So we have a inductance, that is armature inductance plus the back EMF. So, we want for a motor it is a pure DC we require. So, that means the ripple, the current harmonic currents due to the ripple voltage should be as low as possible. So, even though this half wave single phase half wave rectifier is available in textbook, it is seldom used in any application. This is only for understanding the basics of rectification. Now, let us talk about rectification. Also, we have introduced the freewheeling concept. During the negative, this is freewheeling. That means energy stored in the inductor is circulating here. It is like cycle. When you pedal it after remove it, it will keep on rotate, that is freewheel, and due to friction it will come to a stop. Same way the energy stored in this one slowly circulate through the diode and slowly it get dissipated. That is called freewheeling action. Now, let us go to the not the half bridge concept, let us go to the full wave converter. Let us go to the next page. Full wave converter will give higher DC voltage. That means we are using the input positive side as well as the negative side to transfer energy with reduced ripple. So, this is basically a rectification, whether half bridge or full bridge, this is rectification. So, the input AC is rectified and brought to the output. It has DC as well as the ripple content, that is high frequency component. But full wave rectification will give higher DC voltage with reduced ripple. What is mean by reduced ripple? That will once you draw the waveforms and once you study the concept, we will get to know the thing. Reduced ripple means the DC value current along with its ripple value will be much reduced compared to the half bridge converter. So, let us draw the full wave rectifier. Single phase full wave converter. Full wave converter. Single phase. This is a single phase full wave converter. Full wave, what is the advantage of full wave converter compared to single phase? We will state it here. Full wave converter will give higher DC voltage compared to our half wave rectifier. Higher output DC voltage with reduced ripple. There are different configurations possible with this one. Some of the configurations possible with the single phase rectification, full wave rectification we will study, and its merits and demerits we will analyze just for understanding. So, let us take one, full wave with common cathode A. Full wave with common cathode. Full wave with common cathode. The schematic is like this. We have thyristor 1, thyristor 1 I will make it at TH1, then you have the TH2, sorry here not the TH2, here it is D2, let us remove this one, this is D2. We will try to remove that one. Okay. Then comes TH2 because we are talking about the common cathode. Then D2. So D1, D2 here. This is the mains. PAB. AB. We have the load here. We will represent with a DC motor, armature inductance and the resistance. Okay. D1, D2 here. Okay. Let us see how the output voltage ripple, that is voltage ripple coming across the load here, V0 alpha, how it looks. Let us draw our current ripple. We will go to the current ripple, sorry, voltage ripple. This is our VAB, okay. I will also mark the negative of VAB here. This is VAB, this is the VBA, this is VBA. Now, let us take a firing angle here, alpha starting from 0. So, what will happen? Here we will be firing TH1. TH1 from here, where it will go, where it will come to 0 state. So, let us take TH1 is fired. The moment TH1 is fired, diode will immediately forward bias because this point will come here and this is already negative, this diode will conduct. So, here diode will conduct, this D2 will conduct whenever VAB is when this point is negative with respect to this point. That means, during the full negative portion, that is VBA, this point, D2 will be conducting. D2 will be conducting for the negative point. So, when the voltage VAB comes to 0, what will happen? D2 was conducting, TH1 was conducting. Now, what will happen? During this, but we will be firing the next thyristor TH2 here only. There is alpha here, same alpha from the 0 point. That during the VAB negative, we will be firing TH2. So, what will happen? The moment at this point, the voltage has gone negative. The moment it has, that means this point has gone negative with respect to this one. That means this diode will be switched off, immediately D2 will conduct. But for TH1 to switch off, what we have to do? We have to switch on TH2 and make a reverse bias across the TH1. So, until TH2 is turned on, TH1 will not switch off. So, TH1 will conduct for this full period, that is from here to this period. That is, we will mark this point as OP PQ. So, full this period OP, TH1 will conduct from here to this point, up to this point, TH1 will conduct. Now, when this voltage goes negative, that is this point, at this point P, at this point, let us say O, P, Q, this point I will make it R, where the TH2 is turned on R. Then let us make this is S. At point R, here only we will be turning on TH2. So, TH2 will conduct from R to Q. But what will happen during the interval P to R? P to R, VAB, that is A is more negative than this one. So, D2 will conduct, but still TH1 is conducting. So, TH1 will conduct not as to SP, TH will conduct up to this point. TH1 will conduct from SR, TH1. TH1 will conduct full SR duration. But during the P to R, TH1 is conducting. Due to this portion, when this is go negative, the diode D2 will be conducting. During the PR period, D2 will be conducting. Sorry, there's a marking mistake. This is D1. This is D2. So, D2, this D2 will conduct during the when this is positive and this is negative. That is from period O to P. So, D2 will conduct period O to P, the period duration O to P. Diode D1 starts conducting here. So, as long as this point is negative, that is the VA is negative with respect to B, D1 will be conducting. So, D1 will be conducting for the full PQ period. PQ period. And from R to Q, TH2 will conduct. Okay. So, what will be the final ripple coming across this one? When it freewheels, TH1 and D1 simultaneously conducts, the load will freewheel. Similarly, when TH2 and D2 conducts, load will freewheel. That means the voltage across the load is 0. So, during the period when TH1 and D2 conducts, our TH2 and D1 conducts, that time only the output ripple will be coming across the load. That means the ripple, this portion, this hatched portion will be coming across the load. So, with properly placing the diodes, what is the advantage? We can have full wave control is also possible. At the same time, for inductive load, freewheeling action is also possible. Okay, that is freewheeling action when one thyristor, when the diode conducts and the TH1 conducts, the freewheeling. So, during the freewheeling period, the voltage across the load is 0 and the output ripple is coming, or output ripple is appearing. That is all the part of the input voltage waveform is appearing across the output only when the firing angle alpha is initiated for both the thyristors. This is the advantage. What is the advantage? Assume TH1, D2 are conducting, and if the L by R ratio is very high, that is a time constant, L by R is very high, what will happen? Current will not decay, current will decay very slow. So, what happens? The moment VAB goes negative, that is A goes negative with respect to B point, the current will freewheel through TH1 and D1. Now, to switch off TH1, we have to switch on TH2. The moment TH2 is turned on, Now already B has become positive and A has become negative. This TH2 is turned on, and this point, the positive point coming across the cathode of TH1, and TH1 will be reverse biased and TH1 will be switched off. Okay. Now if take a case if the TH2 gate pulse failed, that means due to some mistake TH2 fails, what will happen? Current will keep on freewheel through D1 and TH1, and the load is highly inductive, current will not decay, it will keep on decay, and the next time when the voltage goes negative at the P point, diode will conduct. So through TH1 and D2 it will, as a half wave rectifier, it will keep on supplying power to the load. So what is the advantage? What is the disadvantage here? So we lose control. The moment loss control means output should disappear. That's one thing. But here we lose control at the same time the power converter is supplying power to the load. Okay. So how to avoid that one? What I mean to say, this converter, if something fails, till the inductive energy is there only it should conduct. After that it should slowly conduct and should come back to zero. That's the best way. System should automatically come to stop. But here if the TH2 gate drive fails, we will fail to turn on TH1, and the load is highly inductive, the load will freewheel through D1 and TH1. So how to avoid this one? One way to avoid this one, to give a freewheeling diode. That means don't allow the load to freewheel through the thyristors. Let us go by least resistance path by giving a diode across here. But one problem here is, so when we give suggestions for voltage control, we have to give a cost effective solution. But the problem here is that because of the freewheeling diode, one more additional component has come. Okay. So this will freewheel through this one, but this can be, so we can save on this one diode by changing the configuration in some other way, another modification of this single phase full wave converter. We will talk about that one now. So let us remove this one. Let us go to the next page. Now to avoid one extra diode, also to get the same performance as before without the extra freewheeling diode, the configuration is like this. These are some of the different alternate configurations for single phase converters. So here it is, if you see here, we are not using 4 thyristors, we are using 2 thyristors and 2 diodes. That means only 2 devices only we have control. Other 2 devices, the moment it is forward biased, it will turn on. But thyristor, to turn on, it has to be forward biased, and at the same time during the forward bias period we have to give a gate pulse. So here we have only half the devices only we have the control. So let us have how it looks. See, we will do it in a different way. TH1, then for one limb we will connect thyristor TH1, TH2. The other limb we will connect the diode. Here the load. Okay. So here how the conduction state, let us draw the conduction with respect to our input mains AB. this VAB, and then this is the negative side, that is VBA, VAB and VBA. Okay. Now our firing angle starts from here, alpha. For the next device also, firing angle starts from, for symmetry. So what will happen? This period when VAB is turned on, no sorry, when the VAB is positive, we are turning on TH1. So TH1 will be conducting from this point to this point. So we will mark all the points. TH1 will be conducting from this point to this one, that is this period. Okay. Why? The moment this point goes negative, the moment this is positive and this is negative, we are turning on this one. The moment VAB goes negative, what will happen? This become positive, this will be turned on, it will freewheel through this way. So here, let us mark this is D1, this is D2. So this period D1 will conduct. Okay. So D1 is conducting. Now this VBA, from this point onwards, VBA is conducting. So from this point up to this point, D2 will also conduct. So it will free wheel. So during this period, this is the freewheeling period. Freewheeling period. Similarly, at this point also, this is the freewheeling period. Here what will happen? For the full duration, here, positive duration, D2 will conduct. This is D2 and this is D1. So full this positive period, D1 will conduct. Okay. So what happened to D2 is conducting here. We said during this portion also D1 will conduct. Why? The moment thyristor is switched off, the moment this voltage becomes negative here, what will happen? This thyristor will be switched off, load will freewheel through this path till the next thyristor is turned on. So D1 will conduct this period as well as this period, D2 will conduct this period as well as this is the D2 period. So when the both diodes are conducting, that is whenever the VAB becomes negative, anything slightly negative, this load voltage becomes negative, it will try to freewheel through this way. The moment it freewheels, this load inductance, it will forward bias D1 and D2 and D1, D2 will conduct, and by the time thyristor and TH2 will be switched off. So you have D1 conducting here, and here D2 and D1 will be conducting this period. Let us mark A, point B, then C, D and E. Okay. So during this period, D1 will conduct from here to here, TH1 will conduct from here to this period. That period, when TH1 on, when TH1 and D1 conducts, no sorry, this is marking, this is TH1 conducts and D2 conducts. So let us talk about the single phase converter with the two thyristors and diodes and with a freewheeling diode. So to avoid the failure of one gate pulse, you will lose control of the thyristor as I explained previously. So we can let us draw the full wave converter now here. Okay, this is the diode, this is TH1 and T1. then TH2 and D2. Now, instead of having the freewheeling through the thyristors and diode, we will give a small low impedance path that will connect the freewheeling diode across here. Then we have the load. So, here how the convection happens. Let us draw the waveform. This is the VAB and negative side is like this. This is VAB, this is VBA. Okay. We are firing at this point. We are firing at this point, thyristor 2. So, what will happen? The voltage ripple will be like this across the load. Now, when the firing angle is fired during this portion, what will happen? If load has an energy, it will free wheel through the diode DF. So, this is the DF period. The moment TH1 is turned on from here to here, TH1 is turned on, TH1 will come here, this is positive, the diode will be, this diode DF will be, TH1 will be turned on and VAB the VAB through TH1 come across the cathode of diode DF and diode will be switched off here, and from here point, this point to this point, TH1 will be switched on. And we know this point B is already negative, so D2 will be, diode will immediately forward bias D2 diode and D2 will be turned. So, during this period TH1 and D2 will be turned on. Now, the moment the voltage goes negative, what will happen? This voltage goes negative means the inductive load, because of the inductive load, that slight negative will forward DF and during this portion again DF will conduct. Okay, DF will conduct. Again when thyristor T2 is turned on here, TH2 is turned on, TH2 is on, till this period TH2 will conduct. Okay, TH2 will conduct and here the freewheeling, again the freewheeling, when the till the TH1 is turned on, freewheeling will work out. So, this is a full wave rectification if you see here with the firing angle control. So, here what will be the output load voltage? For half wave rectifier we know it, we have talked about the half wave rectification. We got V0 is equal to V0 alpha is equal to, for half wave it is will be equal to Em by 2 pi into 1 plus cos alpha. Okay. For half wave diode rectifier, diode rectifier, that is firing angle alpha is equal to 0. This implies alpha is equal to 0. So, V0 alpha is equal to Em by pi. Now, this is for full wave rectification. So, the negative side also we are getting the same ripple across the load. So, for the present full wave rectifier, V0 will be equal to 2 Em by 2 pi, 2 times the half wave, 2 will cancel, it will be Em by 1 plus cos alpha. For an alpha is equal to 0. V0 alpha is equal to, for a full wave rectifier it will be Em by pi into 2, that is equal to 2 Em by pi. So, instead of thyristor, if you use diodes for rectification, then what will happen? It will have a output voltage will be equal to Em by pi. Em is the maximum voltage, not the RMS voltage. Em, 2 Em by pi, we will get the output DC voltage. Now, we have introduced the DF. The DS is another, the power circuit, one more diode, that is another extra cost. Can we do away with this DF at the same time that correct freewheeling is ensured? So, let us think about another configuration to avoid DF. Let us go to the next page. This configuration is like this. See, we want to give a least resistance freewheeling path through the diode, not the thyristors. So, in that case, we can have this configuration. Diode we will connect here. AB. So, for the load always it will freewheel through the diode. Let us see how it happens. This is TH1, thyristor 1, thyristor 2, then D2, that is D2 and D1. This is the diode. Okay. Again, let us draw the our mains voltage, how it, this is our VAB, this is our negative VAB. Now, we are here also we are firing with respect to firing angle alpha. The moment TH1 is fired, at this fired we are turning on TH1. So, what will happen? TH1 and D2 will conduct. TH1 and D2 will conduct. So, from this point TH1 and D2 will conduct. Okay. The moment voltage goes become negative at this point, what will happen? The moment this point, that is, the moment this point becomes negative, that is VAB becomes negative, VAB, VBA. VAB goes negative at this point. D2 was conducting, TH1 was conducting. The moment it goes negative and this side become positive, VAB, B side becomes, D1 will immediately conduct and the load will freewheel through this path. So, now here till the next thyristor is fired, D1 and D2 will be conducting this period. This is freewheeling. This is freewheeling. D1 and D2 will conduct till this period. When at this point TH2 is turned on. So, during the freewheeling output voltage is 0. So, during the positive half cycle this much voltage ripple, input voltage is voltage, this much part of the input voltage is coming across the load. Here D2 and D1 will conduct. Now, D1 is conducting. The moment TH2 is turned on. So, TH2 is turned on because A is more negative. The moment, so TH2 is forward biased and the moment this is turned on, D2 will be switched off here. TH2 on, D2 will be off here. So, what will happen? From here onwards, D1 and till this point, D1 and TH2 is turned on. So, this much voltage ripple is coming across the load due to the firing angle. So, this way it happens. This is a full wave controlled rectification. Okay. The moment voltage goes negative here, that means A again becomes positive. What will happen? Till thyristor T2 is fired, till this point, D2 and D1 will conduct. This is freewheeling. So, what is the advantage? The freewheeling is transferred to the diode. Here the freewheeling of the load, it is through the diode. Okay. So, one extra DF, the previous DF is removed, extra DF is removed. Here also the output voltage V0 alpha, that means output V0 DC with respect to firing angle alpha is equal to how much? 2. Here also 2 EM, for half wave it is 2 EM by 2 pi, for half wave EM by 2 pi into 1 plus cos alpha. Now, the other half also, during the negative portion also we are getting the output ripple. So, it is 2 times 2 EM by 2, that is equal to EM by pi into 1 plus cos alpha. This is the output voltage ripple. So, these converters, if you see here, alpha can be varied. What is the range of alpha? Alpha is varied from less than is equal to pi 180 degree, less than or equal to 0. So, if you see from the ripple here, when alpha is equal to pi, output voltage will be alpha is equal to pi V0 alpha is equal to 0. Alpha is equal to 0, V0 alpha is equal to maximum is equal to 2 EM by pi. So, that means by varying alpha, V0 alpha can be varied between 0 to 2 EM by pi. For alpha less than is equal to 0, less than is equal to pi. Alpha varies from pi to 0, 0 to alpha varies from 0 to pi. Alpha when is 0 it will be maximum, when it is pi it will be 0. So, what that is output DC. What it shows, this converter can give only variable positive DC voltage with a maximum is equal to 2 EM by. EM is the maximum phase maximum voltage, peak voltage, not the RMS. But many drive applications, let us take the DC motor drive application, we require the machine to go in forward as well as in the reverse direction also. So, from the DC motor principle we know, for a separately excited machine, if the VDC is reversed, for a particular DC, one polarity of DC, the motor will be running in one direction, the polarity in the reverse polarity, if the motor is running, the motor will run in the opposite direction. So, we require both speed forward rotation as well as reverse rotation. So, many of speed control system for DC motor, this is AC to DC control, phase controlled converters with the firing angle control. These type of converters are called, these type of converters with instead of, even though 4 switches are there, 2 are only controllable. We can only have positive voltages. That means only one quadrant operation is only possible. What is meant by one quadrant? Let us see. if you take the output V0 alpha and output current, that is V0, and we will take V0 here according to my diagram. This is the output current. V0 and I0, V0 is positive, I0 also positive, only this quadrant only possible. But many of the drive application we require all 4 quadrant operation, that is this one, that is voltage is positive, current is negative. Voltage is positive, current is negative. What is mean by that one? The net power is negative. That means load is sending power back to the mains. So, a motor system, when it is rotating, the stored kinetic energy, it will transfer back to the source and system will decelerate. So, this is called regeneration, this regeneration. And as I told, voltage is positive. So, direction is in one direction. Let us take, when the voltage is positive, let us take the direction is in positive direction. So, that is positive regeneration. This is or forward regeneration, forward rotation, positive or forward direction, forward regeneration. So, in that case, this quadrant is called forward motoring. Now, in this region that is quadrant 1, let us take this mark quadrant 2. Quadrant 2 is forward regeneration. Now, quadrant 3, this is both output voltage and current are negative. So, the power is still positive. That means power is positive, power flow is from the source to the load. That means from the source to the motor side. So, it is still motoring, but the voltage is negative. So, motor must be running in the reverse direction. So, this can be called reverse motoring. This is called reverse motoring. Then what is this region, fourth quadrant? That is voltage is negative. So, motor is in the negative direction, but the current is positive. So, that means power is negative. Power is negative, power flow is from the load to the source. So, this is called reverse regeneration. So, what this shows? So, the motor, if the drive system has to work in all 4 quadrants, we should be able to generate negative output voltage as well as negative output currents. But so far what we have discussed, the converter with 2 thyristors and 2 diodes, voltage is only positive and current is only positive. So, these type of converters are called single quadrant converters. Single quadrant converters and are not preferred for any motor drive applications. When you have the high load inertia of the system is there. Why? To slow down the system, we have to take back the energy from the machine. So, power has to be momentarily, it has to be negative. So, it is not possible here. So, let us think about next first. So, it is only on a single quadrant. Let us think about converter. At least we can have positive or forward regeneration. Forward motoring is possible, forward regeneration is possible, or reverse regeneration, or the voltage can go negative. So, let us take from the converter point of view. So, current can only go in one direction because of the thyristor and diodes connection, or even if you use instead of 2 diodes, let us think about using 4 thyristors. So, current can only go in one direction. Let us think about, we can have a negative voltage. So, at least we can have 2 quadrant operation out of the 4. Okay, 2 quadrant means voltage is negative. That means forward motoring and reverse regeneration is possible. How? So, the converter is possible with that one. That means we are talking about current is in one direction and voltage is in both direction. Here we can use, naturally let us see the next change in the converter is instead of diodes, let us use 4 thyristors. So these converters are also, the previous converters are all called semi-controlled converters. Even though we are using 4 switches, 4 devices, only 2 switches are you are using for controlling the output voltage. So it is called semi-controlled converters. Let us take about fully controlled converter. Fully controlled converter will be like this. We remove all the diodes and put thyristors. So we require 4 thyristors to be controlled, maybe, and the load will be like here. So I just generally put a load to show that this load is not purely resistive; it is really highly inductive. Okay. So back-EMF part we are not talking about it now. So I put a simply a load where we can both the voltage can be positive or negative. So let us see whether in this configuration whether we can have both positive and negative voltage. This will be studied in the next class.